Actually, I can
Alright, hey.
Nobody understands that.
Alright, guys, we have about not long, so let's focus here. And let's get after it. What? Not long.
Guys, he's a feeler. Guys, he's a feeler.
Nate? Alright. Alright, open up your books. Let's imagine.
Oh my. Are we imagining a bike that's already on there?
Open your books to make Gilmore!
Hey, look, it's football.
I already did this.
Oh, hey, look, it's Bryce Crab.
Am I coaching
Actually,
football?
Bryce Crab is not in the book. Probably not.
Why?
That is not.
No reason. Look.
Do you want me to coach football?
Yesterday was a 1 year.
I don't know if I can
replace it.
Yeah, but I feel like that would be wrong of me to do that. No one's in
November 24th has some nice. November 6th. It's gonna be. What's on the Monday?
Wait, they're gonna need coach.
It's gonna be.
Anyway, let's not talk about that. Alright. Let's visualize Bryce Crab. No, I'm kidding. Not Bryce. Let's visualize Grandview when they were good. That was okay, so here's what's happening. In some collisions, two objects collide. They actually stick together as they travel after impact. Okay? Okay? In this particular situation, what we have, we're going to have three types of collisions. We're going to have elastic, inelastic, and perfectly inelastic collisions. Okay?
Yeah.
A collision in which two objects stick together and collide after they move together is called a perfectly inelastic. Now think, elastic means they can deform but they come back to their original state. That's what elastic, we talked about elastic, right? A spring you can deform, but then it comes back to its original state. Okay? Perfectly inelastic are ones that deform and stay deformed. And they go together in the same direction.
Can't you only have perfectly elastic and
Yeah, technically none of these are really completely realistic. They only give you a partial picture of the whole thing. I know that bothers some of you. It bothers me too.
Is there such a thing as visco elasticity?
Visco?
I love your
I think I heard it on a kids' TV show once, and I don't.
Oh, what do you think?
I'm not sure.
Kids TV show.
Right. Now we'll talk about all three as we progress, but today we're just going to talk about, listen. Right? Today we're just going to talk about perfectly inelastic collisions, or when a collision happens that the two objects stick together and travel as one object in the same direction. So what this example of the football player catching Odell Beckham style is, they're traveling. You could do this problem as if they were one object with one mass traveling in one direction.
Some say one direction.
Okay? So, with this being said, we will actually have a modified version of the momentum conserved equation, which is going to look like this. So if we say the two objects stick together, we're going to say that these two objects kind of have the same what?
Mass.
Velocity. Velocity.
And what?
Okay? Now you could also say one combined mass too. Isn't that what we're doing here?
Yeah. If they stick together.
Okay? So you could say M total times VF equals all of that. Okay? That would be fine. Guys,
I'm just plugging it in.
What are you plugging into?
plug in your brain.
Yeah, what are you plugging in the cart to? Itself?
Infinite power, duh.
No.
It's in a vacuum.
Guys, sometimes. Alright? So we're going to assume in perfectly inelastic collisions that when they collide, they stick together, they travel in the same direction with the same velocity and a combined mass. Okay? So, let's move on down.
What voice that?
Oh, hey, let's try that. We haven't done this.
Visual concepts!
Stop.
Hey.
You
Ready?
need a plate.
We're gonna do it.
That's all I go.
I'm ready. I'm ready.
But it's not going to remember. It's like a romance.
Collisions of all types occur around us all the time. One common type of collision is an inelastic collision, where two objects stick together and move onward as one object. In these collisions, the final mass of the object is
Boring.
Collisions of all types occur around us all the time. One common type of collision is an inelastic collision, where two objects stick together and move onward as one object. In these collisions, the final mass of the object is the sum of the masses before the collisions. If one of the objects is stationary, the equation is easily solved. Even if both objects are moving, the equation is still fairly easy to solve because the final mass is equal to the sum of the original masses and there is only one final velocity.
Alright. The door just flies up. Now I want to state here, guys, that in perfectly inelastic collisions like this, the momentum is conserved, but the kinetic energy is not conserved.
Because they're all opposed.
Because some of the energy, some of the movement energy, is actually going or being transferred to internal energy when an object deforms. Because you're changing the bonds that are happening when you deform an object.
You're changing the bonds just when you bend it.
Yeah.
Bend it.
You're going to change the length of some of the bonds. You're going to change the energy of some of the bonds. Okay? It's not a huge amount. Okay, but I want you to say that kinetic energy is not conserved in these, but it is conserved in elastic collisions. Okay, assuming you're in a vacuum and no sound can be. For example, if you had two billiard balls hitting each other and bouncing off, okay, those you don't have any deformation that's caused. Okay, and assuming there's no energy being dissipated in the form of sound, you would have kinetic energy conserved. Which we'll talk about that tomorrow. Right, same problem. Alright. Okay, a luxury sedan, something I'll never have. Stopped at a traffic light, is struck from the rear by a struck from the rear by a compact car with a mass. Okay, so we will say that's M1. Okay, the two cars become entangled as a result of the collision. Oh, I'm sorry. I missed that up. I don't know why. M2. We'll say that's M2.
Oh, sick! What?
Sorry, guys. I totally bypassed that first mass.
Oh my word.
Wow, that luxury sedan is twice as massive as the compact.
It's a smart car.
Okay. The two cars become entangled will result in collision if the compact car is moving at a velocity of 22. Compact car is going to be M2, right?
Yeah,
So VI 2 is 22 meters per second.
What happened to VI1?
What happened to what?
VI1 is 0.
It's 0.
Which is it? You guys are literally.
You're hurting his feelings, guys.
Why do I teach?
Here, at least we No, keep
Why in the world do I teach?
To get money to support your
Wait,
family.
what happened?
So we what money?
Keep going. Keep going. I don't
There's
let
a bond
anything
with
ruin
the
your day.
students.
It's literally just.
So if you know the answer, don't tell anybody else the answer.
Yeah, it's true.
Okay? So let's solve this particular problem.
Dude.
Influx variables that
Anything has a C, I,
looking at this, I got a VI1 of 0, so I will cancel out one particular portion of this. Where will it be?
The first.
Now you have all the variables you need to solve for VF. Why do you need me to solve it?
What's the answer? Keep going.
More depressing than Rice and Isaac.
Yes.
Why is VI 22 meters per second?
Because this is the initial speed of the compact car.
Okay, so.
And the compact car is the second car.
Okay.
Yeah. Well, I mean, I could have defined it as the first car, but.
Yeah, I was making sure that was the reason for it.
Yep. So yeah, just take your this divided by that, and you're done.
I got 0.015.
That's
Not correct.
Why? What'd you do?
I multiplied 975 times 22.
Yep.
And then I divided that number by 975 plus 1850.
And you put parentheses around that?
Yes. I literally did.
What's the answer? Move.
I oofed it.
You didn't divide it by 22.
Yeah.
No, it's supposed to be times.
Yeah.
Okay. Anybody else? How much you get that? Or we're too busy doing physics, plutonic
No,
acceleration?
I did it, Crane.
Physics,
The
placenta
answer.
acceleration.
Physical placenta acceleration.
Kramer, what's the answer? Placenta display.
Okay. That one's on camera. Shoot.
What did you say?
Nothing.
Physics placenta acceleration.
Kramer, give the answer.
7.6 meters per second.
Hey.
Actually, 7.59 meters per second. To the north!
Thank you.
To the north! Did you guys put the north on there?
Yeah!
You put the north on there. Hey!
Two clay balls applied head on.
How much time we got?
We have math of that.
13 minutes? Okay, this one's a long one.
Yeah, this is one long boy.
Wait.
I want to do this one.
Alright.
Say it out loud.
Okay. So here's what we're going to do. If you're going to do this on your own, you're not going to say anything out loud. You might as well just be quiet and don't ever talk. Ever again.
Brains the roast.
Alright. Two clay spherical objects collide head on in a perfectly inelastic collision. Okay? The first spherical object has a mass of. I'm going to switch this as bottom. And an initial velocity 4. To the right, so we're going to assume positive direction. The second spherical object has a mass of 0.25 and an initial velocity of 3. Is it negative?
Yeah, because it's to the left.
Great.
You guys are starting to figure out directions. About time.
Not
Great.
negative.
Okay? What is the decrease in kinetic energy during the collision? So we need to find the change in kinetic energy. But in order to find the change in kinetic energy, I probably need to find the what?
Final velocity.
Yup. This is the velocity pretty important in kinetic energy.
Word?
I guess.
Okay, I guess. Why don't you guys solve for the final velocity?
Friends, you're a cool guy.
Go, solve.
Yeah, so when I was on my way back up, I could go way, I could get on my way to.
For what?
Like from, I already fucked up, that was like.
There wasn't.
But I
answers out loud.
Oh, so I should actually do this. I'm kidding.
Roast.
How big is kinetic energy?
Kinetic energy is 1/2 mass times velocity squared.
But what? What does it mean the decrease?
So like
How
the
would you
change.
define it?
So remember, in a perfectly inelastic collision, energy is going to be lost when it deforms. So you're going to have to find the initial kinetic energy and the final kinetic
Yeah, how do
energy.
we get the initial kinetic?
So 1/2 of M1V1 squared.
Well, you've got the initial velocities and you know the mass.
And then you add those together.
Oh, you just combine them?
Okay? Have we all figured out the VF?
Yeah.
What'd you get?
1.6 or what would be the one?
You didn't square 1.6.
Right? We want to find the difference or the change in kinetic energy, so I need to find the kinetic energy initial and the kinetic energy final. Okay, now I have two objects, so I have to add two kinetic energies to get the kinetic energy initial total. Now, we know kinetic energy's equation is what?
1/2
mass times
velocity
velocity
squared.
V initial squared. And we're going to say this is of object 1 plus 1/2 MVI squared for object 2. And we'll have to do the same thing for your final.
Would the final just be 1?
Will it just be the mass?
Yeah.
And then the velocity.
Combined mass.
What's?
So I want you guys to solve for the kinetic energy initial total. And the kinetic energy final should be 1/2. The final velocity is the same for both, right?
Correct.
So if you have your mass, VF squared, this is going to be your what?
Combined mass.
Yeah, or combined mass.
So just one.
Because if you did, right, if you had a combined mass and you did this versus taking mass 1 times the VF plus mass 2 times the VF, it will give you the same answer.
But a big number, I mean like not small.
Is that what you really bet though?
I mean like average. It's like between 6 and 3.
Medium.
That's a big number.
But negative, so it's double. Yeah, that's what I got.
Okay, did we get kinetic energy initial total, or are we still working?
Will you just give us a second?
Okay, I'll give you a second. 1, all right.
Kramer, stop!
Kramer!
Actually, see,
You're one of those students, right?
You're off by 1 decimal point. It's 4.1.
I also normally don't solve.
Then I can pay attention.
Yeah, because I use the whole numbers.
Then Bryce does it all and tells everybody.
Isaac.
I didn't say. I said between 6 and 3 and negative.
What'd you say?
I'm saying I did this right and the book did it wrong.
What did you get?
4.08, negative 4.08. Yeah, it's got 4.07. I got negative 4.08.
I got 4.08, but I plugged everything in correct.
Yeah, me too.
Whatever. Okay.
Isaac and I am right.
So, your kinetic energy initial should be the kinetic energy final.
What? Oh,
So the decrease in energy will be your change in kinetic energy, which will be final minus initial.
Oh yeah, I guess. You know that's so.
What?
The way Bryce runs it.
So what this is saying is you're losing 4.07 approximately. So that that energy is going into going to internal energy of the deformation of the objects that are colliding.
What did it actually?
why is it negative?
Negative 4.0.
Because it's fine.
Because it's losing kinetic energy.
Should actually negative 4.1.
inelastic phase.
I think it was 0.05.
Yeah.
Oh,
That changed a lot.
Okay?
no.
Questions, anyone?
Based on how he wrote it.
Get up there, Lee.
Wait, you guys just looked at the book?
No, the book I wrote didn't say things.
I'm just saying, yeah,
Well, they probably use the addition subtraction rule.
No, like
the book has .250 and this
yeah, you
just
did
has
that
0.25. So like,
okay, compared to this, it should be.
What?
I think
You already have a work set?
I just plugged in my calculator on first, so I just had to do it again.
Yeah, and like, yeah, dude, I try not to look at my grades. The first couple grades.
So this is
Government, yeah.
kinetic energy final minus kinetic energy. And then once you get kinetic energy final, you can.
Oh, I mean, I'm working harder. I got
Alright. Here's what I'm gonna do. I'm gonna find out what one of my parent teachers.
Also, what's flag anyway? Exclamation. Yeah, what's flag?
I don't know.
It's like
Framework, tell my
older name, but it's also like a.
Okay, well if Avery Bush's parents don't come in, I'm free from 5:45 to 7.
Oh, let's go.
That's some good clanking.
What'd you say?
And if Isaiah's parents don't come in, I'm free from 5:45 all the way to 8.
It's okay, we can take a credit. Parents are coming, by the way.
They are?
You said we're going to 2 to 5.
Okay, well, we can take a clank intermission.
Bring our PS4s, hook them up to the projectors and play. We'll be playing Fortnite.
You guys want to do that? That'd be fun.
That'd be fun.
What? No, play clank.
I'd do it. I never played, but
If you guys are here by about 5:30, we can make that work.
Today?
Today.
Oh boy.
let's go.
We're gonna get one.
I just have work to do, but I'll try. I get done with school after this next hour. So.
What are you talking about?
Holy cow. Next hour?
If I do it back
Yeah,
there.
so it's like every day except for.
All I will say is, we'll probably have to take an intermission when I have to have a meeting.
Nah.
But I'm having a meeting with his parents and his parents, so I feel like it's not
It's all
that.
good.
Wait.
But
Well, it's not all good.
it's all.
My mom is how many moms are you doing? 4. My mom always goes like the first one.
I'll probably have to watch this first one.
Oh my word.
Is it like it's like
Just look up the rules after school.
It's
How
like a deck building game.
It's a deck building game along
I also
with
have Megan and
The biggest part of learning it is like bags. You just have to learn what the cards do. Is there a little key?
Is there
like
little
a
pictures
picture?
I can use those?
No, you just gotta read.
No,
it's like playing Dominion. You have to know like what the cards are. But the difference is Dominion you only have like 12 sets of cards, and they're all the same. But in playing, you've got probably almost 150 different cards.
What time? I already forgot time.
I took out, so what I did, Steven, is I took out one of each of those really crappy cards.
Oh, the ones that we.
Which one?
Where are you sure?
What did you take out?
Sometimes.
I really want to
Well, I think I've never won playing that route.
Parents come by, what do you guys?
I'm gonna play that route.
Wait, what time did you say? I already forgot.
6.
5:30.
Jesse, you tell me.
That's why I might get another.
She comes.
Although that might be
Well,
bad.
actually, no.
Just play board games.
What cards did you take out?
Oh, no.
But I like
Lauren, are you gonna come?
Lord, come.
Guys,
Your baby style.
You said you took out cards?
I took out, so there's like 3 or 4 different copies, and there's 2 duplicates of them, so I just took out.
Let's go. Oh, it's literally.
I can put them back in.
Yeah.
Hello.
Yes.
You want me to change? premarital strife going on right now?
No, she just wasn't getting the answer.
Let's stop here looking at
You're just not giving me answers. Let me show you how it works.
Great.
I'm kidding.
I found a girl in London that was my cousin. Oh, your girlfriend?
Please, no, because I'm dating a boy and Jacob, and my uncle's name is Jacob. And so he's like, oh, you're dating your uncle? No, that's so weird.
Where's Roby? I need to thank you. Roby!
It was good. I was like gassed up for 4 months, but it was good. You guys play folklore?
Yeah, what was it?
You had a girlfriend. Katie, you had a girlfriend?
Today, I mean.
Katie had a
today.
girlfriend?
But like yesterday we just like, is that our one?
Lock the door.
Yes.
This is our stuff?
Where's the sucky calves right now? Okay, you think it's just a vase? You really believe that? I'm not sure I don't know what I think yet.
I can't wait for
I feel like this happens a lot with LeBron teams. But like, I don't know. Do something after school or
well, one thing that I actually did do.
wait, no, I need to learn this word. I forgot about that.
Everybody's gonna go. Whatever new character comes out, they always do that.
No, Thursday's a worksheet, Wednesday's a notice. What?
Yes. Pretty sure that's like Becker Feldman. That's like Becker Feldman in my sister's class. Like her next name Macy tells me that like she'll be like, am I right or am I right? That's what it is.
Mr. Alice.
Yeah. This
I was right.
He's a random.
That's the same assignment.
Do you mind if I name
Alright, there is a bell ringer, believe it or not. There it is. So, fine. Hey, bell has rung. That means you do the bell ringer. It rang, you ring it. That doesn't make sense. Anyway, answer the problem. I'll get that in a second. Okay? Trusty.
Is this his one or two?
Probably. He forgets his name here.
Is that his?
Shoot.